Hi everyone, my name is Michael Misha Mikhailo, and I'm a Scala developer. You might wonder, what am I doing on a Ruby meetup? I ask myself the same question. So right, thank you. So today we are going to talk about mutable state and concurrency with actors. Give me a second to check whether these things work. No, doesn't look like that. Okay, anyway. So a little preface before I start. In this talk, I'm going to expose the problems behind multithreading and not multiprocessing. So yeah, for Ruby, default approach is to go with multiprocessing. It's like multiple processes. It's like using unicorn and cron with a rack for a background job processing. But despite that, we have plenty of options to make our application thread safe. So to make our application threaded. So here are the most commonly used tools. It's a Sidekick for background job processing, which uses thread to handle really a lot of messages. Puma, which is web server designed for concurrency. And yeah, by the way, it was designed for Ruby News, but it works pretty cool in JRuby. Scene, well, I'm not sure it's threaded, but it has an option in configuration. Threaded equals true, so probably it is. And the Torquebox. Torquebox is actually a pretty crazy tool. It's a wrapper on top of JBoss, which is Java JBoss, which allows you to write allow you to write a JRuby applications and deploy them as a servlets. That's pretty much it, but there are plenty of options for multi-threaded programming in Ruby. So before actually going to a problem, I want to make a generic overview of differences between multiple processes and multi-threading. It's really top level, but still it might give you the idea. I hope you guys can see it. Yeah, it's fine. So the first point is that multiple processes use a lot of memory. I believe you've seen that. Every time you deploy a unicorn application, start like 12 workers, it will take somewhere around 1 gigs of RAM, for example, or 2 gigs of RAM. So threads are much better in terms of memory because they don't copy environment and they are pretty much more lightweight. Yeah, and the second is that multiple processes is much slower to create and destroy. Of course, it's not a noticeable delay, but still, whenever you try to fork a process, it takes some time. And if you write your application, if you write an application that dynamically spawns in new processes, it might be really slow. And there is obviously no such problems with threads because, well, in most implementations they're fast. And we don't usually create threads in the middle of execution when it comes to JRuby. We usually create them at the beginning with a thread pool, so it's even faster. Multiple processes is much easier to code and debug. We'll see an example of that in next few slides. But in general, it refers to that a process doesn't have shared memory. So if you have if you have an allocated memory to the process, the only point it could be changed is inside of this process. And the problem behind threads is that it has really a lot of shared memory, and that's actually the topic of this talk. Multiple processes have the drawback that it has a risk of creating a zombie process. So how it works, when the parent process exits before children dies, we will get a process that will exist forever until it will be manually collected. So and there is obviously no such problem with thread because if process dies, all the threads, it takes the threads with it. So regarding memory, we already discussed that, but yeah, process has its own virtual memory space, when the threads share same memory space. And that's actually the topic of this talk. And the most big disadvantage of a multiple processes approach is that it requires inter-process communication, which is pretty hard to design, especially if you don't have a solution, ready-to-go solution. So yeah, the easiest way to do that is with a 0MQ or Unix pipes, but you still need to invest a lot of time to design it properly. So in terms of threads, we can communicate via shared memory. Of course, it's not that easy to do, but it's still much easier than to design inter-process communication. So before I continue, I want to ask how many of you guys worked with multithreading in production? Mm-hmm. Okay, is it like, do you guys work with JRuby, Ruby-News, or JRuby? MRI. Okay. So cool. So yeah, let's start from the simplest problem, but the biggest one that lay down behind the multithreading applications. So yeah, this is a classic example of race condition. Well, let me be completely honest, it was copy-pasted from Wikipedia, but it gives you a great overview why multithreading code is really hard to debug. So what's happening here? We have a global variable counter. We have two threads. Each thread increment counter 10,000 times. Then we wait until thread join and get value of a counter. In this example is 6,489, but in reality it's really hard to predict the actual value of a counter at the end. So I believe it worth to show you an example. Yeah. I hope it will work. Yeah, you see, the first time is 6,000. It's pretty much the same code. Second time is 15,000. Yeah, so basically it's absolutely unpredictable. It will have absolutely unpredictable value. So again, this problem is called race condition. So why that happens? Basically, this is what interpreters do. First of all, thread 1 reads the value of a counter, thread 2 reads the value of a counter, then they increment them inside of thread memory and then try to write it back. So this basically means that increment operation is not atomic, or we can say that it's not mutually exclusive. So the expected behavior for us in this case would be something like that, right? So wait until thread 1 will finish the job, and then and only then go to a thread 2. So since this problem is really it's really easy, it has been solved like thousands of times, but here's the most common option is to use Mutex. Well, again, there is another option which is based on a atomic integer which encapsulates increment as an atomic operation, but it requires additional gems, so I decided to go with Mutex. So what the Mutex is, how it works. Well, can you have you guys read the code? Basically, we just add a global variable called Mutex and wrap all the access to shared resource into Mutex synchronize. That's pretty much the same. By the way, I can give you an example how it works. Yeah, how it's TC with Mutex. Yes, as you can see, we will get the expected result all the time. Right, so Mutex allows us to make this operation mutually exclusive, which is basically Mutex stands for. It's a mutual exclusion. So the point of mutual exclusion is to ensure that there are no two concurrent processes in the critical section at the same time. Basically, that's the way to ensure that we're not modifying our shared memory at the same time. Usually, Mutexes in programming languages refers to a semaphore, which is one of many implementations. They're like message passing is an option for Mutex, is a Mutex device, semaphore, lock, recursive lock, things like tuple space, and I don't really remember a lot of them, and the message passing, which we will see in future. So yeah, the easiest way to explain what semaphore actually do is to show the code sample. Yeah, it's pretty simple, but it has a queue, it has a blocking queue, and it has a method called synchronize, which accepts a block and run it whether queue is available. So yeah, I can show an example how it works. Yeah. But it's actually better to make a small overview of what the queue is. So yeah, take a look on this code sample. We have a queue. It's not a standard queue like in any other programming language with two functions like pop and push. It's a bit different. It's we use it mostly for multithreading in Ruby. So the point of it is to queue pop is actually a blocking operation, and it blocks the execution until queue is empty, or until element appear in it. So can you see this example, guys? Queue new, thread new, sleep for 1 second, then push message hello, and main thread expects queue to have a message there. So let's run it and see what happened. Yeah, it hangs for 1 second and then print hello. That's basically what queue does. Do we need to talk a bit more about queue here? Because it looks like the implementation is pretty clear, and okay. So this was a simple problem, which was pretty easy to fix, but we don't have problems like that in our applications. So here's an example of a bit more complex problem. So the first problem here is extending of active record. It's like this single line of code. I don't know. Is there anything like pointer? Okay, this single line of code like extends active record base can make absolutely any class absolutely not thread safe, not synchronized, and basically destroy any multi-threaded application. Why is that so? First of all, active record brings a lot of implicit state to a model. It's a ID, created at, updated at, and other properties which are pretty much okay. Yeah, this class, which are pretty much hidden from a developer. So let's start from a single operation, which is debit. Basically, what it does is withdraw amount from a balance. It's pretty simple, the same example we've seen before. So here's an example of, well, you've seen it. Here's the example, the same we have with increment. You see, it's quite hard to predict the actual value of bank account at the end of execution. Well, it's not critical. It wasn't critical for auto increment, but it really is for a bank account, right? So there is a quite easy way to fix it, but yeah, somehow like that. So we can introduce Mutex for a model, since it's not an atomic class. We can just bring it as an instance variable, and then wrap any mutator to a synchronized block. The only point here is that we never have a single mutator in active record model. Usually, it implicitly creates a lot of accessors, and if you want to make your model completely thread safe and completely synchronized, you need to override all the instance classes to make it, well, thread safe and synchronized. Again, as I already told, you need to wrap all the values. How it looks like, somehow like that. So it's hard work to make your active record model, to make instance of your active record model work in a multi-threaded environment. So yeah. The second problem is that Mutex or Semaphore is bringing a lot of complexity to a model. It starts from overriding all the accessors, and it ends up with unexpected effects. The most common unexpected effect with a semaphore is a deadlock. Well, deadlock is not really a common case, but it's still nice to be aware of it. So take a look at this slide. It's not really a real banking operation called swap, but it can give you a good understanding of what deadlock looks like. So we have a swap which acquires, we have a swap function that acquires a lock in a thread number 1, right? Bank account swap acquires a mutex number 1. Then we have a second thread which acquires the mutex in bank account number 2, the same one. Bank account number 2 tries to swap the bank account number 1, and mutex of bank account number 1 is already acquired by a thread 2. The same thing happens vice versa. This code will hang forever, probably. I mean, it's really hard to predict, but at some point it will hang forever. Yeah, so this is all about the object state. But with active record, we got another issue. We got a resource state problem. So it's pretty common issue that is already fixed in active record base class, but still we need to keep track of a version all the time. You don't really need concurrency for that. So the fix for this problem is called optimistic locking or pessimistic locking or whatever. And what it, by the way, the interesting fact that community suggests to block positive transaction while you're doing that. It was quite weird. So how does optimistic locking looks like? We just, every time we save our object, we just check the current version in database. If it's the same, we save the object. If not, we throw an exception. So what are the downsides of this approach? Well, pretty much the same. Few of them are the same as with Mutex. It brings additional complexity to a model. When you have an active record, it's not really a problem to add a version property to a table and then just implicitly check it over every time you save it. But whenever you work with a third-party service or I don't know, and you can't modify it, or database table is not really modifiable, it's a real problem. Also, you need to have a nice throughput of a database to handle that, because it makes a select all the time, it performs a version check. The second problem is that it doesn't really solve the problem. So, I mean, it's not a fix, right, to throw an exception. What's the point? Yeah, and because if it throws an exception, we need to design a recovery strategy for it. I mean, if it's a user, of course, we can show a validation error like please submit your application or something like that. But if it's third party, if we are designing an API and we have a client, I know like another web service, it might be a real problem to throw exception. So yeah, this is why optimistic locking is not always an option. There is a third problem with active record. It's called non-atomic methods. Right, so this is my favorite. The first one is a find or create by ID, which will almost always fail in concurrent environment. This happens because find or create by ID or find or create in general is not really an atomic method. First of all, it performs find. So yeah, we just have two threads that runs the find or create by ID with the same ID. So yeah, we have two threads. And that's actually what's happening. You just find bank account with ID 1, find bank account with ID 1 again, and then save it 2 times. So expected behavior is not really to get an exception of a unique constraint violation, right? So that's just one of the many examples. The second one is a really common is uniqueness validation. Basically the same problem. We create bank account with account number and in first thread, and then we create bank account with account number in second thread. And if you don't have a unique constraint on database, you can potentially come out with two same records, two records with the same account number. Again, that's why it happens. So thread number 1 initialize model, thread number 2 initialize model as well, then validation performed, well, and of course it will return true because there is nothing in the database, and then both of models are being saved. The one throws exception, I assumed that there is a unique constraint. So yeah, imagine the case like that with a validation of bank account. It's really hard to predict how it will behave, but I'm pretty sure it will throw the exception. So and it's obviously not an expected behavior. So you see, this is a pretty much simple cases we use all the time in our applications. Nothing special, nothing like, well, it's pretty standard. But the conclusion we can make that whenever we use a standard Rails stack, or whenever we use something with a hidden state, it's pretty hard to make it thread safe, make it concurrency ready, multi-threading ready, excuse me. So yeah, here's the conclusion. We can't do anything about it. Have you ever tried to override the static active record method? It's like crazy. That's even more, I tell you that try to override active record constructor. It's crazy as well, because you never know where it's defined. Okay, so actually we can pick a different multi-threading model, and it will help a lot, and it won't fix the problem, but it will bring us a different vision of of resource management and entity management. So the topic, actors. Actually, actors is pretty much the same as Mutex. Well, it is a Mutex in some ways because it works with the message passing, and message passing is one of the Mutex devices. So what the actors actually is. A lot of text, I will try to explain everything. So actor is a single-threaded primitive of concurrent computation. It's always single-threaded, so all messages passed to a actor are processed in a single thread. Not exactly the one, but in a single. It can receive messages, so it's message-driven, how to say that, message-driven approach. So if you worked with a queues or IMQP protocol, you're already familiar with what this message-driven means. Actor can make a local decision. We'll see that in future. Actor can create more actors. Well, yes, that's so. It can create more actors, and it can send more messages. And I don't know if you guys can see, but I make this line, this last line, it starts to work again. Yeah, it's gray, because we are not going to show this in current example. It's quite hard to feed a changing of behavior in 10 lines of code, so we're only going to concentrate on the first one. So let's start with the simplest implementation. With the simplest implementation of actor probably possible, I don't know. So here it is. I will go through each method later, but for now you can see the big picture that it's pretty simple, right? It's like we have a process, we have a tell method that push message to mailbox, and we have a constructor. That's pretty much all. So mailbox. That's a very important thing of the very important part of an actor. It's basically like we've seen an example before. It's a blocking. Well, it's not always a blocking, but that's basically a storage of all the messages this actor have received. Yeah, and it's pretty easy to send a message. We just push a message to a queue. So nothing harder than that, I believe. The second one is a behavior, the method process. You see why it has sender and a message. It's the same. We push. Sorry. The same we pushed in a tell message, so basically message and sender, and then we have a process with message and sender. So it determines what kind of message it receives and decide how to react to that. So it makes a local decision with a case statement. It can change its private state. You can see it increment counter, and it can send more messages. That's what happens when sender tell. When a get message arrives, we just perform a sender tell counter self. The interesting thing here, you might notice that sender has a method tell. That's actually the point that there is no single actor doesn't make sense. There should always be at least two of them, because we need to send message somewhere. So the third part is basically a core of any reactive application. It's event loop. Usually, event loop doesn't look like that. Usually, event loop is a complex structure, but that's pretty much the spirit. So we have a single thread which processes all the messages in an application and then just push it to processing somehow. So let's take a look on the simplest actor again. We have a counter, mailbox, event loop. Then we have a method tell, the only job of which is to push message to mailbox, and then we have a process. It's pretty clear, right? Anyone have questions so far? No? Okay. So let's send a message. You see, we have 10 threads, which sends 200 messages to our counter actor. And the nice thing about that it actually gives us expected result. So I can demonstrate it. Yeah, as you can see, the final value of a counter is 2000, which is exactly expected, which is the expected result for us in this case. The only thing that it's impossible to await for actor to complete his work. So yeah, your application should be asynchronous, but we will talk about this a bit later. So basically, what's happening here? Thread 1, the only job of thread 1 is to push message to a queue, the same as thread 2. They basically bring more messages to a blocking data structure, and that's all. It's doing nothing more. And actor thread is the one that processes them. Since queue as a structure is synchronized, it's full of mutexes inside, we are completely safe to run this code, and it will work in exactly the same way. All the call to a counter tell will be processed synchronously. So basically, this is the same actor. The only thing I have extracted the process method from it. So yeah, that's a common abstraction, because the only difference is how we react to the messages. So yeah, it looks like that. Yeah, and I introduced a stop method just to give the ability to stop the actor. So it was a really simple example of what the actor can do. Again, it has a mailbox. It has its own event loop. Well, usually not, but in our implementation it is. And it can react to a message it receives. So, but it was a simple case. And again, our application not usually looks like a counters. Usually we have models, and these models have race conditions and stuff like that. So here's a bit more complex example. This is a bank account actor, which works with the same bank account model but without mutexes. So you can see that it's pretty much the same. We have a internal state, which is ID. We have a process method that knows how to handle only one message called debit. Every time it receives this message, it grabs the bank account from database, debit amount, save it, and send it back to sender. Send the change structure. So that's all. You see, we just gain the possibility to get rid of all the mutexes from the model, because actor is mutex by itself. and it processes all the operations in single thread. So there is no risk that we will get into troubles with that, right? Quite simple. So a key point that a mutex is moved to a different layer. We can call it middleware, like an actor middleware. That's all. We don't need to care about thread safety and locking in the model. We can only care about it on a middleware in actor, and it simplifies our applications a lot. And the other benefit is that active record can be used in concurrent applications, which is a great progress. Again, the second problem we already talked about is that we don't have additional complexity, and we don't have a risk of deadlocks. Even despite that, this risk is not really common, but we still don't have it. It's pretty cool. So basically, the point of actor is to gain the access to a shared record in a single-threaded manner. That's how it works. So it's not only the one problem it fixes. We can get rid of optimistic locking as well. So it's done with a sink which becomes a pattern. It's called actor router. Actor router is a sink that stands in front of standard actors and decide what to do with a message. It has a envelope structure which should have a hashing key, and the actual messages should be forwarded. So take a look on this code sample. It's pretty easy. We have a private state called registry, which is basically a hash. We don't need a synchronization there because all the messages are processed synchronously. And we have a method process. It checks out whether the message is an envelope and forward it to a corresponding actor. Okay, so as soon as we introduce this entity in our system, we are completely safe to process all the operation on a single bank account with single ID in a single thread. Yeah, I have a picture to illustrate that, but I'm not really good at presentation, so it looks like that. Thanks Google Docs for nice tools. So caller is actor. Caller call bank account router with some kind of envelope and bank account ID 1. It will be routed to a bank account 1. Caller 2 doing the same. It calls bank account router with a bank account ID 1. It will be routed to bank account 1 and bank account actor 1 will process all those messages synchronously. The same thing with actor 3. Well, and caller n is basically a illustration that it can be routed wherever it's possible. So also interesting thing about that you don't need bank account router to respond to a caller. That's the conception of forwarding we've seen a bit earlier. You see, we don't actually use self as a sender. We get self from a message we received. So yes, that's a forwarding. We don't even know about existing of a bank account router here. Okay, so non-atomic operations. How to get rid of a problem with non-atomic operation in case of active record. So do you guys remember that we wrote a bank account model with a, how it's called, uniqueness validation. So it was non-atomic and it causes a lot of race conditions in the multithreaded code, but we can introduce the create bank account actor and encapsulate everything underneath. So basically we have a message, we get this message and just create the bank account and send it back. Of course, we can have multiple create bank account actors, and it will bring the same problem. We will need to introduce some kind of I don't know, the optimistic lock in here. But it's better. But it's a common pattern to have only one actor that responsible for a resource operation. Something like that. Unfortunately, actor model has its downsides as well. So the first downside is that it's almost impossible to fit it into synchronous flow. You see, we don't actually have a response, right? The only thing we have is a message that is sent back at some point in time. So yeah, if you have a rack application, it's most likely that it would be impossible to implement actor models there. But if you use event machine, everything should be fine. Well, at least I hope so. The second problem with actors is that it might decrease throughput for some operations. Yeah, what does that mean? Imagine that we have a create bank account actor. And we have a requirement to create 10,000 bank accounts, right? We will send 10,000 messages here. And all of those messages will be processed synchronously. So they are not parallelized anyhow. So operations like that are basically, well, they're slow because they are single-threaded. The other problem, as the biggest one, that actors requires a complete change of the whole application design. I mean, it's just not possible to fit actor model in a standard model view of controller, because, well, you have a middleware of asynchronous actions, and you need to bring some kind of a bridge between asynchronous and synchronous application. In Scala, it could be a promise. Well, generally speaking, the promise is a really good candidate for that, but Ruby doesn't have one. So yeah, those are the biggest downsides of actor. Of course, there are much more of them, but still, we solve this problem with a really small amount of efforts. We solve a problem with a global mutable state in a concurrent application, but it has its own downsides. So there is no silver bullet. Of course, someone might say that software transactional memory will solve this problem, but I encourage you to try it. It's almost impossible. Also, these actors are pretty easy to implement, and they not looks like the one we use in production, right? It's usually much more complicated. And currently, I decided to write a learning example of an actor system in Ruby, which is pretty simple. It just takes a bit more code, so it's impossible to fit it into slide. And if you are interested in taking a look on this example, just ping me, and I'll send it to you. Any questions, guys?
What do you think about celluloid actor system?
Mm-hmm.
There is a library called celluloid.
Celluloid looks, yeah, it looks pretty interesting, but you need to compare it to other actor system implementation. So on the one hand, we have a celluloid, and on the other hand, we have OTP and the akka.
Well,
So
unfortunately.
well, actually, yes. I made an experiment. I took a JRuby, and I've tried to integrate it with akka. It works pretty fine. The code was ugly, but it works pretty fine. Sure. Any other questions, guys? Not only about actors, about multithreading. No? Okay then. Thank you.